Hi, it's my pleasure to be here giving my 12th PyData conference talk. So I'll start with a brief introduction of myself. My name's James Powell. If you'd like to follow me on Twitter, I'm Don't Use This Code. This is a theme that you'll see throughout this talk. I guess at some point you get the privilege of being able to give a talk without giving a title, so this talk has no title. In fact, this talk has no title, no slides, no organization, no story, it's just some code. And some cool code. But before I start, some of you may recognize me, and some of you already kind of know what to do when I say my name. So I run NYC Python. It's the world's largest and most active Python meetup group. You may have seen me at an NYC Python event. We have events every week, and we have large events, nights of talk, every other Thursday for about 100 people. You may have seen me in August at PyGotham. It's a conference that I chaired. Actually, some of you in the audience were speakers there. It was a really awesome event. I think we're going to do it again in 2015. You may have seen me at a conference that I ran independently of NYC Python and PyGotham in March of this year called For Python Quants. That was a conference for people like me who work in the quantitative finance field. If you'd like, you can see me next week at the next version of this conference in London. And if you'd like to see me by video, this conference will also have video tickets. You may have seen me at the very first PyData talk that I gave in 2012, or the follow-up to that in Santa Clara in 2013, or in Boston, or in New York in 2013, or sometime this year in London where I spoke, in Berlin where I spoke, in Silicon Valley where I spoke, or today here in New York City. So that's a little bit about me. Let's get into the CPython stuff. So I take Don't Use This Code very seriously. So I'm going to show you some neat code, but please don't use it. There is a message behind it. It is somewhat interesting, and it can lead to something productive, but be forewarned, it may not necessarily lead to something productive. So I'll start with something really simple. All of you in the audience should be able to kind of look at this and figure out what's going on. I have some object called foo. It's of class foo, and I type foo.baz. Uh-oh, I spelled something wrong. I meant to type foo.bar. And it gives me this nice little attribute error saying that foo doesn't have a baz because I should have typed bar. I wrote a module called DidYouMean. And DidYouMean, you can see the code here is exactly the same, except at the top I import DidYouMean. It adds just this little thing at the bottom. Maybe you meant .bar. And how does it figure out what you meant? It just takes all of the attributes and the dir of the object and figures out what has the shortest Levenshtein distance. But that's pretty simple. But I think the cool thing about this is, how did I do it? And to really light that fire under you, I'm going to show you a little bit more. It works with getAttr. So I must have done something kind of weird to make it work with getAttr. In fact, if you capture a reference to getAttr and then import my module and then try this again, it still works. So I must have done something really weird because I'm not just overriding getAttr and built-ins, I'm doing something a little bit deeper than that. In fact, it works with all the built-in types. So I must be doing something really wild. It'll work with all the built-in types, it'll work with the function type, it'll work with both old style and new style classes in Python 2. So I must be doing something really weird here for this to work. In fact, you might say, well, he must be using sys.accept hook, and he must be catching the attribute as it percolates up to the top layer. So here's an example in an unmodified Python 2 where I capture the exception, and you can see it prints out the exception. And here's the example with mine where it prints that out. So I must be hooking really deeply into CPython in order for me to be able to insert my little DidYouMean, no matter how you try to access this attribute. And so let's see how I did it. Well, the first thing you might do if you wonder how I did it is you might do an ls on this module. You'll see, oh, there's a couple of C files, so I must have written a C module. And if you look into it, you'll see, well, this is a C extension module, so I must have done something a little bit low level here. And in C extension modules in Python, we know we have a PyInit module, we have this standard boilerplate, and you see this little thing called hook function. And what is it hooking? It's hooking PyObject_getAttr. And it's replacing it with a hooked PyObject_getAttr. Well, it turns out your CPython interpreter has all of these standard routines for doing all of these standard things. So you call getAttr on an object. And inside your CPython runtime, it calls PyObject_getAttr. You call length on an object, and it does PyObject_length. And these are all inside your CPython in some binary that's running on your computer. And what I did was I wrote this little thing called hook function. And what hook function does is it says, I'm in an extension module that's been loaded after my CPython has started running. But I can visibly see all of these functions that CPython exports, because module authors should be expected to be able to use things like PyObjectGetAttr or PyObjectLength in order to implement their own functionality. I find that part of the CPython interpreter, and it's somewhere in memory. So I unprotect the memory page, because it's probably in read-only memory. And I take my function, which has a little no-op at the top, and I move a little bit of assembly around to add one little instruction, which is a pop rack. So I wonder what that means. And then what I do is I smash it with some new memory that looks like this. So somewhere in your running CPython image, you have PyObjectGetAttr. That's part of the compiled CPython. And I find that, and I just put in a couple of assembly instructions to say, no. We're not going to run this code over here. We're going to run this code over here. And then I'm free to do whatever I want. And as you look through it, I can do pretty much whatever I want. In fact, in addition to that, so I have my own little getattr here. And it's the exact same getattr that your CPython runs, except at the bottom, if you get an exception, it just calls distance, which is Levenstein distance, and it tries to figure out what you really meant. And it can insert this behavior into this get attribute call no matter how you try to access it. Because you have no ability, as a Python programmer working at the top level, to intercept this code path more deeply than I do. So I have inserted my behavior into your running CPython without you having to write any C code or having to recompile your interpreter, do anything that you want in this fashion. Now, this is an interesting and perhaps powerful technique. The question is, where does it go? And it may not go anywhere. It's not terribly useful. So let's take a look at maybe another thing that I did. Because I did that, and then I got a little bit bored. I used to give a talk called Embeddings of Python. And I talked about what happens when how do you embed Python into a C application. So you have some large runtime, maybe a trade system that's written in C++ or written in C. And you want to use Python as an extension language. You want to write plugins, or you want to model deals really quickly in Python, and you want to interact between these two systems. In fact, just today I was having a conversation with somebody who said, I'd love to be able to embed Python into SAS so I can interact with my data in SAS using Python. And I said, it turns out that embedding Python into another application is pretty easy. There are, in the standard Python documentation, a very high-level embedding and a pure embedding. And depending on what you need to do, you can use either the pure embedding or the very high-level embedding in order to get this done. If you look at my talk, I go through some of the steps and some of the implications of one type of embedding or the other. But the question that dogged me, and the question that drove me to learn about that, was, can I embed a Python interpreter into another Python interpreter? Because maybe I have a Python 2, and I want to run some Python 3 code, so I'll just embed a Python interpreter and run it in this subordinate interpreter, and I'll be happy. So your first intuition might be, well, Python 3 is shipped as a shared object. So I have a Python 3 shared object, and this is in my Python 2, and I'll just use dlopen to open it up in PyInitialize. I segfault. And this is something that we rarely see in pure Python code. I've actually done something so bad that the interpreter can't even catch the error, the whole thing just crashes. You can see I'm dumped right back down to my shell. So it turns out that it's impossible for you to embed a CPython into a CPython, because both your Python 3 and your Python 2, or maybe your subordinate Python 2 into your host Python 2, they have a lot of global state. And when your Python 2 interpreter starts, it tries to smash some global states, tries to initialize some things, and the host interpreter has already been initialized, and it all goes to hell. And you might confirm that to yourself and say, well, I'm using a dlopen, and maybe I can play with some flags. So I look at my man page for dlopen, and there's all these flags here. And you can try RTLD global, and RTLD local, and RTLD no load, and all that, and it still doesn't work. And you might say, well, I want to prove to myself that it doesn't work. So instead of writing Python code using C types or CFFI to try this embedding, I'll write some C code. And in the C code, I'll load up a Python 2 using dlopen, and I'll try loading up a Python 3 using dlopen as well. And I'll try to link this, and I'll try and run it. And when I try and run it, I'll run into the exact same error. But if I'm clever, I will scroll down one more layer in my man file, and I'll see this really interesting flag called RTLD deepbind. And what RTLD deepbind does is it allows you to take a shared object and load it in such a way that when that shared object looks for symbols, it doesn't look outside of its own context. And when you do that, you realize that, in fact, it's not impossible to embed a Python interpreter into a Python interpreter. It's very easy. All you do is use dlopen with RTLD deepbind, and it works. So let's take a look at that. And you can see here, This is a Python 2 and a Python 3 running simultaneously in the same process space. They could share memory. They could do anything. They could interact with each other directly. And all this code does is it prints out the version info, and it prints out the process ID just to show that I'm not fooling you at all. So you have two Pythons running in the same process space. But if you're like me, you might say, that's not enough. Now that I've solved this problem, what more can I do? And you might ask, can I run multiple Pythons inside of Python? And it turns out you can write code that looks like this that creates maybe a struct of Python interpreters. And you try and run two Pythons and two Python 2s and two Python 3s inside a single C application. And you might write a little bit of code here, and I wrote a little bit of code here to make sure that there are actually two independent or four independent interpreters. So with this little code here, what I do is I try to import a little library. I import itertools, and then I check, is itertools in modules? That's my way of setting some global state and then checking, oh, was that global state set? And I know if the interpreters are the same, then if it's all just the same interpreters being loaded, then that global state will persist over each one. And if it's not, that global state will be independent. And when I run my code, I see something that looks like this, and I can interpret the true and false for you. The true means that itertools has not been loaded in sys.modules, and the false means it hasn't. So you can see here in my example, my Python 2, when I first load it up, the global state is unset. When I load up my second, supposedly independent Python 2 interpreter, the global state is set. So these are, even though it looks like I have multiple Python interpreters running inside a CPython, that's not the case. It turns out that DLOpen, when you try to load a shared object that you've already loaded, will just say, no, you already loaded that one. I'm just going to give you a handle to that existing one. And so it turns out you can't embed multiple Python interpreters into a C application. But I wanted to figure out how, but before I try to figure out how, I thought, I've embedded Python 2s and Python 3s. Can I embed a Python 1 in there as well? So on a plane flight back from the conference where I first showed the CPython's interpreted, I came up with this. I built a Python 1.5 shared object. And here you can see an application using the DLOpen trick that's not written in C, but it's actually written in Python, using C types in order to use DLOpen, that embeds a Python 1, a Python 2, and a Python 3 into a single interpreter. But that just doesn't answer my question. How do I embed multiple Python interpreters into themselves? Now note, I said how and not why, because there is no answer to that second question. Well, it turns out that DLOpen can't do it. Every time you try and DLOpen something, it'll say, you've already loaded, I'm just going to give you a new handle. And it turns out if you read your man page, like the good boy that you are, the good boy or girl that you are, you'll see, well, there's nothing there. And you can see this DLOpen library gives you DLOpen, it gives you DLErr, it gives you DLSim. But if you're dogged in this, you might start reading the source for your linked library, for your dynamic linker. And in that, you'll see, wait a moment, my header files don't define this, my man pages don't describe this, but there's this weird call in there called DLMopen. I swear I'm not making this up. You have a DLOpen call and a DLMopen call. What the hell is DLMopen? And it takes this really weird flag in the beginning called linker namespace. Well, it turns out there's another call in your linker, if your linker happens to be gold or happens to be the one provided by libc, which probably for most of us running on Linux is the case, that allows you to open a shared object in a separate linker namespace. And so you end up with an example that looks like this. This is a C application that can use either DLOpen or DLMopen to try to load a set number of Python interpreters into a C application. Here I'll try it with DLOpen, and I'll say I want 3 Python interpreters. And you can see the location of all my interpreter handles. So all of these interpreter handles are in the same location. They're all the same. And if I just change it to DLMopen, now I have 3 separate, completely independent Python interpreters. But the question is, what about global state? Are these really separate? So here, let's get some, yeah. Here, I'll try it with a little bit of test code. And my test code looks like this. I'll use a C library called locale. And locale can set some C global state. It's a library that is wrapped by Python, but it's a library that exists independently of Python as a pure C library. And it has the ability to set and get a locale so that you can do some automatic locale translations and lookups and whatnot. In my Python interpreters, in each one of them, I'm going to query what the locale is set to and then set it to something else. And we're going to see what happens. So, got to run it with command. And you can see, in each case, it'll print out what the locale is, and then it'll set the locale. And in each case, the locale is uninitialized when I start up that interpreter. What this means is not only are these Python interpreters completely separate with their own completely separate internal global state, but any libraries that they load themselves are also separate. It's a namespace after all. It just happens to be a linker namespace that is completely undocumented that nobody seems to know anything about. So what you have here is an example of an ability to load multiple Python interpreters and have them do completely separate tasks. They're all in the same process space. They're all able to pass memory between them. You can control them centrally. They're not in separate, they could be in separate threads if you want to. They're not in separate processes. They're not in child processes. They're all in the same process space. And they're completely and totally independent of each other. Now, what could you use this for? I don't know. But it's pretty cool. And it turns out if you can do it in C, then you can do it in CFFI. So here's an example of the exact same code, but instead of writing some C code, I write some CFFI, and I just take the headers, I just take the prototypes of the functions, and I just open up libdl myself, because CFFI doesn't give me access to dlmopen, because nobody gives you access to dlmopen, because I don't know if anybody ever uses dlmopen. And then I load a Python 2, and I could load multiple Python 2s, and I have this thing right here that tries to load a Python 2 recursively inside itself. So the Python 2 then tries to load another one, tries to load another one. At some point, it'll fall over. So there is still one area that's not been covered. But you can see with this original example, you can load 10 Python interpreters into themselves until you run out of space in this so-called static TLS block. And if you try and load 16, you'll run out of linker namespaces. So there's still a little bit of work to be done to maybe patch your dynamic linker to allow you to embed multiple or infinite Python interpreters into themselves. But what this goes to show is you have this process where something is said to be impossible, and you don't accept it, and you search and you search and you search and you search, and you end up finding that it's possible. And not only is it possible, but it's pretty trivial. It's just one call to one function with one argument. It's probably pretty weird. So I'm going to show you the last example. And this last example is called the bang bang. And let me make this, okay. So this is a little bit of Python code that we may be familiar with. We have some function f, and it multiplies two things times each other. And those two things happen to be constants. ASDF is a constant, and 10 is a constant. And let's disassemble this and see what happens inside. Well, on every invocation of this function, we're loading this one constant, loading the second constant, and multiplying them. But ASDF never changes, and 10 never changes. But we're doing this redundant calculation every single time we call this function. So that's exhibit A. Let's take a look at exhibit B. We import the datetime module, and we create a date inside our function. And this is something that we often do. We have these literal types, or we have these constant values in our classes. They may be SQL query statements. They may be datetime objects. They may be some rich object. But notice that this date is static. The three arguments will never change, and the date object is, in this case, we can, for simplicity's sake, consider that it's immutable. But you can see I made a bug here, because there is no 30th of February. And yet, my code is not telling me this is wrong, even though it could look at this and statically say, well, this is wrong. It turns out that in this case, Python confuses, or Python combines the idea of scope as the visibility of a name and the execution context. Because when Python looks at a statement like this, it'll say, okay, class foo. So I'm going to create a code object, and at the end of the creation of the code object, I'll do a build class. And inside that code object, it'll say, I see a function. So I'll create a code object for that, and at the end of it, I'll do a make function. And Python will, line by line, execute this, and it won't be able to determine that this invalid date is invalid, because you have to run it. And so this is one of the limitations of Python, that scope as visibility and scope as evaluation context are conflated. What we'd really like is to be able to say, this variable here exists in this scope, so nobody else can see it, so that if we're looking at some large function and there's some variables inside it, that those variables are only used in this function, so we can change them freely, but we don't necessarily want them to be evaluated on every run of that function. Now, one typical technique that we might use is we might do something like this. We'll create a const value at the top level, and we'll say, return const value. And this is a very good approach, except you can see it gets ugly. And as we have more and more of these const values at the very top level, our top-level scope is going to be really dirty, because if somebody imports our module that has this, and they do a dir on our module, they'll see all our consts, and we'll put an underscore in front of them to say, well, don't really look at this, but it's still going to confuse them, it's still going to add a lot for them to think about. And it's still not going to be that fast, because this is going to be a load global. So you probably end up writing it even uglier to get some performance back. You do something like const value, you make it local, and then maybe in a tight loop you might say something with const value, with the underscore version of it. So what I did was I added a little syntax extension to CPython, and I call it the bang bang because it has an exclamation point, which is in programmer parlance a bang. And so what it does is, when you add an exclamation point in front of a statement, it compiles that into a code object, takes the AST and compiles it into a code object, and that code object has a special name bang. And when CPython sees a constant bang expression, when it's about to evaluate a function, one scope up, what it'll do is it'll evaluate it and statically store the result. So let's take a look at our original example. Here, we have this expression, just as before, multiplying two constants together. But this bang expression, the semantics of it are, this value has this scope as visibility of inside of f, but as evaluation, it's evaluated one scope higher. So when we disassemble this, instead of seeing ASDF times 10 for every time we run this function, it'll already have been evaluated one scope up, and we'll see just the constant value. So here we just see load const of the value. And bear in mind that this is faster than our example where we wrote the constant out ourselves, because load const is always faster than load global. Load const is an array lookup. Load global is a dictionary lookup. I told you there's going to be some wild black magic hackery. But here's our other example, where we had this date object that was a constant date object, and it didn't warn us. Well, here, we evaluate that date as a constant, one scope up, and so when we evaluate this class and construct this class, it'll warn us immediately that this is an invalid constant. So you can see here, it gives you a warning. And that's something that you might actually want. You might want to be able to add static checks to your code to say, before this code is actually run, or before this helper function is run in some tight loop, what I want you to do is I want you to evaluate it and determine if certain preconditions are met. What you might also want to do is you might want to do this more richly than CPython already gives you. So CPython has a peephole optimizer, so it'll already fold some constant expressions. Integers added to each other, it'll already fold. But in this case, we're trying to calculate the roots of a simple second-order polynomial. And we as a programmer know that if we give it fixed values, that this function's pure, and the result will always be the same, so we can add this bang expression at the beginning, evaluate it one scope up, and when we disassemble this, we can see we store just the constant value. Because we know as a programmer that we can decorate this and say, this is a constant expression, it only ever has to be evaluated once, and then for the rest of the lifetime of my program, that value is going to be the same. We can get a little bit of both safety and speed from this. And you can think that we could apply this in some very interesting ways. So here, I have two functions, one called fastPath and one called slowPath, that perform some optimization. And maybe the fastPath requires a certain specialization that the slowPath does not require. Here I have a helper function inside the function that I call, and it's going to reach into its closure and call either the fastPath, it's going to determine what the best function is. And it'll use it in this tight loop here 1,000 times. So my return value will be whatever the best function is applied to my two input variables. Well, the semantics of the bang expression say that I can write it in this fashion, and I can determine on the creation of this function once and for the lifetime of my running program what the best path is. And so if I as a programmer can say f is only ever going to be called with ints, use this fastPath, and that'll be held for the duration of my program. Now compare this to the tracing approach, or compare this to the inference approach, where the compiler has to infer for you what the best types are. The compiler could always be wrong, or your mechanism for inferring could always be wrong. And so that inference mechanism always has to have a safety valve where, well, maybe I was wrong, maybe these weren't ints, and some path there. And it has to add some complexity from that, and it has some limitations. Whereas in this approach, you're directing Python and saying, if I was wrong about this assumption, it's my fault, I'll change the code myself. And so you can end up getting some very similar optimizations that you could from an inference approach without having to add the same sophistication and complication that you do from the inference approach. Because you as a programmer can say, I know my data, I know what's going to be fed into it, I know you can use this fast path. I just don't know until I'm just about to run it on my data which path it is. So that's the bang bang. I'll show you how I actually implemented it. It turned out to be very easy. So the bang bang turned out to be about 430-something lines of code. And it took me about 3 days to do. One of those days was spent on a flight back from PyCon Spain. And you can see I touch a couple of different parts of it, only 8 files. I make 8 changes to 8 files in order to implement this. And how did I do this? Well, I made one change to the grammar, and then I ran it, and I saw what happened, and I read a little bit here, and I read a little bit there, and I had to kind of run around to collect all the information about how the different parts of CPython worked. And after a while, I collected it, and when you look at this code itself, it's really, really dinky. I mean, all I do is I add in my bang expression to the grammar, and then for the AST, I add a section to set up some constants. Most of this is boilerplate. I add my tokens in here. I add a little preamble here where I say, okay, if you see it, evaluate it. And that's it. So you may look at all of this hackery, and you might ask yourself two questions. The first question you might ask is, what's wrong with you? That's a very good question to ask, and it's not a question that I can answer. But you might also think two things in your mind. And the one thing that you shouldn't think when you look at this is you should not be impressed by this. It's kind of interesting. It's a little bit novel, but it's not impressive. In each case, it was really just the order of, the first case was 5 lines of assembly, 5 assembly instructions. Maybe even you could measure the amount of code in bytes. And the second case was 1 function call. And the third case was 400 lines of mostly boilerplate C code. Now, if you're going to tell me that you're horrified, then it's okay to be horrified. And it is more than okay to be horrified by all of this. My underlying point in the message that I want to convey to you is, as part of NYC Python, and in part of organizing PyData and events like this, you often are put into a situation where you find people who have done very, very impressive things. And not to downplay the impressiveness of some of the projects, but I personally believe that examples like this show you that technology, that programming, that open source is available and accessible to everyone. And I will close with a personal story from my own life. So I am a country boy from Texas. I grew up in Texas. I don't live in Texas. I love Texas. I came up to New York to work, but I'm a Texan at heart. I have never in my life ever sat in one Spanish class. And yet, when I was in PyCon Spain, I could kind of understand what was going on. I could see an exit sign and say, oh, it's an exit sign. I could ask where the bathroom was. And how could I do that? Well, I was in an environment where I was immersed into the use of the Spanish language, and you could kind of pick it up, and you absorb it after a while. When I went to university for a degree in liberal arts, and my degree was in Asian studies. Before I started university, I could not have told you the difference between Thailand and Taiwan. And by the time I was finished with my university, I could speak fluent Chinese. And the reason for that was I went to class every day. I went through all the exercises. When I would speak to the professors, I would try to speak to them in a language. They gave me some feedback. They said, you know, we really want to encourage you guys to learn. And every single person in my class, who were all just country boys like me from Texas, we got to a very, very high level of proficiency in a language which many people consider to be impossible for an English speaker to learn. And how is that? Well, it's the exact same situation as with programming. If you want to learn this stuff, it's very simple and it's accessible to you. It's out there. It's just code. And in many cases, even some of this wild stuff is only a couple of lines of code. It's there for you if you want it. You have to put in the effort. You have to put in the time. And sometimes it may take a lot of time and a lot of effort. It took me 4 years. But if that's something that you want to do, you should look at this and you should look at the stuff that you see at this conference and say, that's impressive, and I want to make that kind of impact myself, and I can make that kind of impact myself. And the question is, just like learning Spanish versus Chinese, Spanish is easy to pick up in Texas because you're surrounded by it. Chinese is very difficult to pick up because you don't have the same access to resources, to people to speak to books, to movies. So what do? You have to seek that out. It's the same thing with all these code examples. Some of this assembly hacking is hard to find. I had to seek it out. I'd spend days doing research. So how do you do that for programming? And that's the point of this conference, and that's the point of things like NYC Python. NumFocus, the foundation that runs PyData, is here to provide the resources to you, to connect you to the people that you want to know, the people who have the same drive and the same desire to learn. It's there to help you do as much as you want with this technology to fulfill any ambition that you have. Because all of this is just within your reach. And it's something that I find personally very empowering. Organizations like NumFocus and locally to New York, organizations like NYC Python are here to make something like this look trivial to you, to say, I could have done that. It's just a couple lines of code. I just had to read this book and this book. And to know which book do I have to read? And to know who you need to talk to and to connect you with people who are maybe working on similar problems who you can throw ideas against. That's the point of all of this. And this is why I like events like PyData so much. This is why I love NYC Python. This is why I love this community. I'm really, really impressed with everything that's been put together here. And I'm just so eager for everybody of you in the audience to just have the opportunity to come to the same realization that I have. So that's a little bit of code, a little bit of wild stuff. It was my impromptu, untitled PyData talk. I hope you enjoyed it. Thank you very much. I think we have time for between 0 and 1 questions. Hannah? Oh, you can already use it in IPython notebook. You can actually even go to tempmb. You do tempmb.org, and you go to tempmb.org. You just do pip install digimean, and it pops up for you. I don't think it's very useful, but the really cute thing about that is since I can arbitrarily patch any part of CPython, my bang bang hook I can make as a module importable syntax extension. It could be developed into something useful. I'll say that that's outside of my purview. I'm here just to do, I'm explicitly here to do stuff that you shouldn't find useful at all. Any other questions? Okay, thank you so much.